Hello students, in the last session we saw 5 different laws. They were like law of multiple proportion, definite proportion, conservation of mass, and then Avogadro's law, Gay-Lussac's law. We saw all those laws. You should be clear with those concepts. Same way, we concluded it with one atomic mass unit, right? So what is how to define one atomic mass unit? We did see that understanding behind it. In this session, we will do the average atomic mass and then the mole concept. Everything will be done in this session. Same way, we'll see some important chemistry terms that we need to know, which will be like molarity, molality, mass by volume percentage, things of that sort. Got it? So these will be the concepts that we will discuss in this session. Okay. Now let's jump into it. So here I've got average atomic mass. Fine. So in the last session, we have already found out what is meant by atomic mass. Atomic mass is nothing but you take a carbon atom and then divide its mass by 12, you'll end up getting one atomic mass unit. Now what we are going to find is average atomic mass for particular element. Got it? So when you look at the nature, if you consider carbon, it will not always have like 6 number of neutrons into it. Generally, to differentiate between one atom with another atom, what we will count is we'll count the number of protons. Got it? So if you have like 6 protons into it, we'll call it as carbon. If you got like 7 protons into it, that is nitrogen. So that is how we'll do the periodic arrangement of the elements, isn't it? Here, when you look at the nature, you have got like 3 different types of carbons. So all the carbon had same number of protons into it. So when you have the count of proton to be same, then we can consider it to be same nature element because it will have the same property while doing the experiment. But the point is, in all these 3 cases, the number of count of neutron is differing. Okay, so when you get such a kind of situation, we'll be able to consider these carbon as isotopes. So the term isotope represents you have same number of protons but different number of neutrons. Got it? So we have got like 3 different isotopes of carbon. So in the first case, that's the normal one where you will have 6 protons and then the 6 neutrons. In the second case, you will have like 6 protons but 7 neutrons. The count of one will be greater. And with the case of third carbon, you have got 6 protons and then the 7 and then the 8 neutrons. Okay, so these are considered as isotopes of carbon atom. So generally, if you have more count of neutrons into it, obviously it will become unstable and the element will be radioactive in nature. Got it? So it will easily disintegrate and become the other element. But in this situation, these 3 are much more stable when compared to the okay. So if it was like C615, that is not possible in the nature. Got it? So as if now we just know like 3 different types of isotopes with respect to carbon. Got it? So let me write it. You have got isotopes. So these are the 3 different isotopes. So in the case of isotopes, what will be same is it will have same number of protons. Then obviously neutron is going to differ. So here for isotopes, you will have same number of proton. Got it? It should be clear. Then see, when you look at the nature, you do the experiment, you do the measurement of mass through the Bain-Bich mass spectrometer experiment. When you look at the inference, it will be obvious some of the mass of the carbon atom will be greater when compared to the other mass, right? So based on its availability, we have formulated this table, right? So you do not want to worry about the experiment they have done to figure out this abundance. They have given you straight away, which is like C12. This is the normally present carbon atom, which will be like 98.89 percentage, which means if you consider like 100 carbon atom, out of which 98.89 carbon atom will be like C12. Got it? So that's the percentage. And then that is called as relative abundance. That much amount of carbon will be present if you take 100 grams of, 100 gram or 100 atoms of carbon, right? So this is a normally available carbon atom. Same way for the C13, it was like 1.108 percentage. C14 is actually a radioactive carbon. So that carbon will be present in a very small quantity, which will be like 2 into 10 power minus 10. Got it? So if you look at the atomic mass unit of those carbon isotopes, the normal one will obviously be 12 because that was a standard that I fixed to measure the atomic mass unit. Therefore, into 12 will give you like 12 U. But in the case of C13, that will be slightly heavier than the number of nucleons count, which will be like 13.003 U. And then for C14, it is like 14.008 U. So these are experimentally found data. Got it? So they are given as the data. What they are asking us to find is, when you do the experiment, we will not be able to tell that all the atoms are like C612. Got it? We know that some part of C13 and C14 will be present in the carbon that I'm going to consider while doing the experiment, right? So whenever you take carbon, I'll have to find the average atomic mass which I need to substitute over there, right? So to get the average atomic mass, what will I do? So whenever we have to find the average, what we will do, we'll just multiply this 12 with the parameter that we need to find, which is like mass over here, with its percentage, right? So here the percentage for the first one will be like 98 percentage. So 98.89 divided by 100 will give you like 0.9889, right? Things of that sort. So 12 into 0.9889 will give you the, with respect to unity, it will give you the consideration for 12 C12, and same way I'll have to add it with the next available carbon, which is like C13. So I'll have to convert it to percentage or with respect to unity, and then multiply it with 13.3003 EU, right? So that is how generally we do the percentage. So now they're asking us to find the average. What we will do, we'll just multiply it with the percentage and then add all those parameters. With respect to unity, you will end up getting the average atomic mass in this situation, right? So the basic math understanding that you need to know, right? So if I do multiply those two stuff and add it, I'll get the average atomic mass, isn't it? So let me do the multiplication over here. So with the case of 12 C12 carbon, you have got 0.9889 into 12 U, right? So that will give you a value that is less than 12. Got it? Because it is not 1 into 12U, based on its abundance, I have just reduced that value, which is 0.9889, close to 1. And then I'll have to add it with the next available carbon, which will be 13U. So that should be equal to 0.00108, isn't it? Yeah. You have 0.00108, 13U, and then the final one will be like 2 into 10 power minus 12. Okay, so 2 into, this is a very meager small quantity, right? 2 into 10 power minus 12. Here I'll have to put the C14 mass, which will be 14.008 U, isn't it? So here it will be like 14.008 U. With the case of C13, that should be 13.003 U, isn't it? Yeah. So here it should be something like this. That will be like 13.003 U. Fine. So if you do the multiplication and the addition of all those terms, you will end up getting 12.01, which is like close to 12. Fine. So if I consider the average atomic mass of this one, that will be like 12.01 U. So based on its relative abundance, I just found, based on its percentage of availability, I just found the average atomic mass. So here it is like 12.01 U. If I just approximate it in this situation, I'll be able to approximate it with like 12U. Got it? There are some specific situation with respect to different other elements like chlorine and all those other stuff, where we will take like in decimal places. How you should actually understand that one is, based on its abundance, we have did the same way average atomic mass and then found a value that is not a kind of whole number. It could be like intermediary answer also, right? So that's the understanding that you need to know. You could get the atomic mass to be like 35.45, something like that. If that was the case, then how you should actually consider is, they have found out the average of different isotopes and then they have given us the average atomic mass. Got it? So that's how we need to consider. With the case of carbon, it is not a problem because it is something like 12.01, which I would be able to approximate it as 12U itself. Got it? So this is how we will have to find out average atomic mass for all the elements that needs to be considered. Got it? Yeah, you shouldn't have any doubt. Next, what we are going to do is we will have to find the molecular mass. So molecular mass actually means, you here the name itself clearly suggests I'm not going to find the mass of one particular atom. Here it is in molecular state. It could be a compound or it could be a molecule. That's not a problem over here. Molecular mass actually means when you have like two atoms combined together. In that situation, when it forms a molecule, I'll consider a molecular mass. Let me find out the molecular mass for the CH4. So how should I actually do this one? So here in this case for the carbon, that's going to be 12.01 U. That's the average atomic mass that we found out, isn't it? Same way, with the case of hydrogen, that will be equal to 4 into 1.008 U. Yes, right. So if I do add these two stuff, it will be like 12 plus 4, which will be, yeah, 16, isn't it? So we'll get 16 point somewhere close to 2 or 3, something like that, 0.03 u, 16.03 u. I'll be able to approximate this one as 16 u. Fine. So if they're asking us to find the molecular mass, this is how we will have to do it. Just consider the individual atom and then I'll have to add the masses of all the atoms. You will end up getting the molecular mass. That's it, simple one. Next, I have just given you one more example into it, which is like water. Okay, so for the water, how should I actually do it? So here you have got oxygen. So the oxygen, first let me consider the hydrogen. So that will be 2 into 1 u, 1.008 u. That is approximated to 2 into 1 u. And then for the oxygen, you have like 16 nucleons into it. You'll have 8 electrons, I mean 8 protons and then the 8 neutrons together. You'll have like 16 nucleons. So in majority of the situation, the number of count of nucleons will be equal to the atomic mass unit. Therefore, in this case, you will have 16 times 1. It's the same thing, right? Yeah, 1 into 16 u, whatever it is. So now you have got 18 u. So 18 u will be the molecular mass of the water. So if I have to convert it into the standard unit as a unit, then what should I do is I'll have to multiply it with one atomic mass unit, isn't it? So 18 into 1.67, no, 1.66 into 10 power minus 27 kg will give you, into 10 power minus 27 kg will give you the mass of one molecule of H2O in terms of kg. Okay, this is such a minute quantity, so while doing sums I'll not be able to carry this 10 power minus 27, 10 power minus 27 again and again in the sum. Therefore I'll just match it with a natural number, which is like 18 in this case. So 18 u. Got it? So here this is how we need to get the molecular mass. It's just the same way that we find the atomic mass, right? So in this case, it is a molecule, which means a combination of atoms. Just count all the atoms with respect to its masses, atomic mass, just add it, you will end up getting the molecular mass. Simple one, straight away one. Then you have got something different into it, which is called as formula mass. Fine. So finding formula mass and then the molecular mass, both are just the same thing. But the only difference over here is these kind of molecule doesn't exist in the nature, which means in gaseous state. For example, let me take NaCl. Okay, so this is the common salt. I have taken the NaCl and then I'm just going to heat it. Okay, so if you just heat it to a considerable temperature like 300 400 degrees Celsius, I'm just approximating it over here. So if you're just going to heat it to such an high temperature, what will happen is chlorine will start separating from the sodium. Okay, so here I've considered NaCl. When you heat it, the chlorine will get converted to gaseous state and then it will start vaporizing as Cl2 molecule, right? So as a diatomic molecule. So NaCl will not exist in nature in gaseous state. If that was the case, I'll not be able to separate one Na and Cl in a combined state. That's not possible. In these kind of situations, so these kind of situations generally arises with crystalline solids. Got it? So these NaCl will just combine together and then it will form an ionic compound. We'll learn ionic compound, all those things in upcoming chapter. As if now, what you need to know is when some combination doesn't exist in nature in gaseous state, in that situation I'll just consider it to be like a gas and then I'll find the molecular mass for it. Fine. Okay, so that is what is meant by formula mass. So formula mass and molecular mass both are just the same thing. Only notion is this stuff, formula mass compound will not exist in nature in gaseous state. So that's the only difference, nothing else more to it. So here crystalline compounds don't exist in gaseous state, in gaseous molecular state. So these kind of molecules will not exist in nature in molecular state. So if I have to find the formula for formula mass for these kind of chemical compounds, you will get Na, which is like the the formula mass, I mean the atomic mass for sodium will be like 23. Okay, so you will have like 11 protons and then the 12 neutrons into it, so that will give you like 23 U, a kind of 23. Got it? Then for the chlorine you'll have 35.5. Fine. So while doing sums, you'll get used to this atomic mass unit, right? So you'll end up by hearting all those values. Anyway, do not worry about the numbers. So for the sodium it's like 23U, and then for chlorine it is like 35.5. Or I have already told you the reason why you got like zero point 0.5 into it is because I've just found the average of all its isotopes. I ended up getting like 35.5. That's it, finished. So this is average atomic mass that I'm substituting. So 23U and 35.5U will give you, yeah, let me do the addition. So that's going to be like 58.5U. Yeah, 58.5U will give you the formula mass for the NaCl. Got it? You should be clear with this stuff. So formula mass and then the molecular mass, both are just the same thing. Only difference is this exists in crystalline form. It will never be in gaseous state. I'll just consider if it exists in gaseous state, what will be its molecular mass? That will be equal to, considering one sodium and then one chlorine, I'm just adding it. That will be the formula mass over here, right? You should be clear with the concept of formula mass. This stuff is done. Then we will see the mole concept. This is the new concept that you need to know. That's a very important one which you should know. Got it? So let's see mole concept. Mole concept will be handy in the real-time scenarios. Got it? So while doing a chemical experiment in a lab, I'll take the compound in the ratio, in the measurement of grams. Got it? So that will be the standard convention to pick some chemical compound that is needed for the reaction. Got it? Kg is actually a lot of quantity. That's not possible. When you do experiment, that will be a small scale amount of compound that you are going to choose. So gram will be a good unit to pick particular chemical compound, right? So when you do the experiment, I'll have to get to know the understanding of the atoms, number of atoms or molecules in it, right? So here the mole concept, if, with the concept of mole, what will I be able to do is I'll be able to figure out how much number of atoms or molecule is in that chemical compound with respect to the amount of compound that I've chosen in terms of gram. Okay, so I'll get a relation. So how much amount of atom is there or molecule is there is something that I'll be able to get it, right? So to get this one, see, if you consider one atomic mass unit, that's a very small quantity. So with respect to such a small quantity, I'll not be able to choose so little bit quantity of chemical compound to do the experiment. That's not possible, right? Therefore, I just need to know if I'm going to take like 2 gram or 10 gram of carbon, then how much amount of atom should be there in that 10 gram. That's what I need to get, right? So that will be handy. If you consider 6 into, if you consider something like this, 1.6 into 10 power minus 24 kg, that's not possible to choose from that chemical compound. That's not possible, right? Therefore, in the real time situation, I choose molecule, I choose that particular substance in terms of gram. So I'll have to match it with the number of molecules or atoms present in it, right? So to do the matching, what will I do is, generally I'll consider carbon as my standard atom, isn't it? Standard to measure like atomic mass unit. Therefore, I'll just stick to carbon itself for the first simplistic situation. Here, I'll just take 12 grams of carbon atom. So that's the quantity that I'm going to choose. So choose, okay. So I have just taken 12 gram. So this 12 gram of carbon atom is easy to get while doing experiment, right? So 12 gram is actually a correct number of, it's not like 12 kg. That's a huge amount. That's not needed to do a simple experiment. Same way, very small microscopic quantity is also like very much less. So gram will be a good parameter. Here I have taken like 12 gram of carbon atom. So what I need to get over here is in 12 gram of carbon atom, how much amount of atom will be present. Okay, so in 12 gram of carbon that I've chosen, how much amount of carbon atom will be present. That's what I need to get. So 12 gram divided by mass of one carbon atom. If I just divide it with mass of one carbon atom, obviously I'll end up getting the number of carbon atoms that is present in it. Okay, so to get the mass of carbon atom, what will I do is I'll just divide it with 12 into 12 u will give you the mass of one carbon atom, but in this situation I just need to substitute with the term that I've put in the numerator itself, right? Because I'll have units has to be same, isn't it? So here 12 into what was the mass of one atomic mass unit, that will be equal to 1.66 into 10 power minus 24 gram, right? If I do solve this one, I'll end up getting the total mass. I'll end up getting the number of atoms of carbon that was present in 12 gram of carbons. Okay, so this will be equal to, this number will be equal to, if I do the math and if I solve it, this will be equal to 6.023 into 10 power 23 atoms. Got it? So when you take 12 gram of carbon atom, you will have like 6.023 into 10 power 23 atoms into it. Fine. So same way, if they have given you like 14 grams of nitrogen, so carbon, next you will have nitrogen in it. So in nitrogen you have got the mass number to be 14, which means you have got like 14 nucleons into it. So if I take like 14 grams of nitrogen, so that was its atomic mass unit also, 14u. Okay, same way if I do divide 14 gram divided by 14 into 1.6, I'll end up getting 6.023 into 10 power 23, right? So whenever we do the experiment in chemistry, we'll consider it in terms of moles, not in terms of atoms, because it is a very small quantity. Okay, so in the Gay-Lussac's law, while doing like Avogadro law, I've just considered it like two parts of oxygen, like two parts of hydrogen, one part of oxygen, isn't it? So in that situation, two parts actually means 2 moles of hydrogen, which means you have got like 2 into 6.023 into 10 power 23 molecules. Okay, there hydrogen, it was in diatomic state, therefore I'm telling you like 2 into 6.023 into 10 power 23 molecules, which will be equal to like 2 gram of hydrogen, right? So in the real time situation, I'll not be able to count all those microscopic atoms in it. Instead, I'll take in terms of gram with respect to the mass number, right? So for 12 gram of carbon atom, you'll have 6.023 into 10 power 23 atoms. Same way for 14 gram of nitrogen, if it was like atom, then you will have like 6.023 into 10 power 23 atoms in it. So this is the understanding that you need to know regarding the mole. Okay, this notion has to be clear. So the number of carbon atoms was equal to 6.023 into 10 power 23 atoms. Fine, this idea has to be clear. Same way, if they have given you like what is the molar mass of H2O, they're asking us to find the molar mass of H2O, which means I know the the mass of one H2O will be equal to 12. I have already found it, right? 16 plus 2, that will give you like 18u. So that will be the mass of one molecule. So that is nothing but the molecular mass. Here what they are asking us to find is molar mass of H2O, which means it was equal to 18u. Instead of u, I'll have to substitute 18g. So in 18 gram of H2O, I'll have 6 into 10 power 23 molecules of H2O, right? So that's the idea that you need to know. So molar mass of H2O will be like 18 gram. So to get the molar mass, it is like simple. If you just know the mass number, you'll be able to get the molecular mass. So from the molecular mass, instead of u, you just put the g. That will give you the molar mass. So gram will be a good convention to stick to while doing the chemical experiment, because that's how much I'll be able to take it in a real time situation, and that is a feasible quantity, isn't it? Fine. So that should be clear. Same way with the case of NaCl, I just found it already. That was like 58.5 over there. So here that will be equal to 58.5 gram. Got it? So 58.5 gram, 58.5 gram of NaCl will have 1 mole of NaCl ions in it. Okay, so 18 gram. If I have to write it, I'll be able to write it in this fashion, which is like gram per mole. So 18 gram will contain 1 mole of H2O, right? So same way here also, I'll be able to write it in this fashion, which is like gram per mole, right? So this is something that you need to know regarding the molar mass. Fine. So molar mass, molecular mass, formula mass, yeah, all those things are kind of similar one, but only thing is I'll just change this U to G with the case of molar mass, because when you put like gram into it, so that will give you 6 into 10 power 23 units are there in that gram. So that's what that actually represents. Fine. You should be clear with this idea that I've told you, right? You shouldn't have any confusion in that part. Next, let me find it. So this is with respect to the gram mass. Okay, so mass is getting involved over there. With the case of gaseous state, I've already told you gases are very much spaciously arranged, such that if you consider like a one football, the entire playground is a kind of empty one, which is vacuum. So if that was the case, with the case of gaseous molecule, the mass doesn't come into picture. Fine. So if it is such so and so spaciously arranged, then in that situation, volume will be same irrespective of the atom that you are going to choose or the molecule that you are going to consider. So that is what is meant by Avogadro law, which we have already seen, right? It doesn't depend on the nature of atom or molecule. Got it? So whatever molecule that you choose, same set of volume will have same number of molecules or atoms in it, right? So that's Avogadro law. It should be obvious. Therefore, in gaseous state, to take 1 mole of atoms or molecule, I need a volume of 22.4 liters, right? We should have this number 22.4 by heart. We'll use it again and again while solving some. So 1 mole will be equal to 22.4 liter. Okay, 1 mole will be equal to 22.4 liter in the standard temperature and pressure situation. Fine. So if you are going to pressurize the gaseous molecule, then that's a completely different scenario, because we are just going to pump lots of gaseous molecule in a small chamber. In that situation, you'll have more molecules. Okay, so in normal temperature and pressure, which means surrounding temperature and pressure, standard temperature and pressure, which is generally considered to be like 0 degrees Celsius, 1 atmosphere. Fine. So you have got like another one convention, which is normal temperature and pressure. So that will be 20 degrees Celsius, again same 1 atmospheric pressure. Fine. So whatever the situation it is, there is just a slight change with respect to temperature, which will not produce any significant change with respect to 1 mole. Therefore, whether they give you like STP or NTP, doesn't matter. You can just approximate it always to 22.4 liters. So 22.4 liter of gaseous molecule, whatever molecule it could be, will contain 1 molecule number of atoms or one mole of atoms or molecules in it. Okay, so 22.4 liters will give you like 1 mole of molecules or atoms in it. Got it? So that's the understanding that you need to know, right? So while doing Avogadro law, I told you like I took 2 parts of H2, right? So if I have to take like 2 moles of H2, then obviously I'll have to consider 44.8, because 22.4 will give you 1 mole. Same way, 44.8 will give you like 2 moles of H2 molecule, right? So that's the understanding that you need to know. Got it? So you should be clear with this idea of molar mass. Molar mass is nothing but the same molecular mass that we have already found. Only thing is you'll have to change that U to G, because this is the real time situation. I'll not be able to take compound in such a microscopic quantity. That's not possible. Therefore, I'm just going to take it in terms of gram. So to match that with the same range of other reactant that is needed, I'll just take that gram to be my standard units. Okay, so if gram was such and such, then I'll have to match it with the same number of atoms with respect to the other molecule. So this U could be changed to G, with which I could actually map it easily, right? You should be clear with all the stuff that I've told you. You shouldn't have any doubt in it. We have almost come to the last part of the session, which will be the percentage of composition that we are going to find it over here, right? So here I'll take H2O. Got it? So here, if I have to get what was the mass percentage of H2 in this water molecule and what will be the mass percentage of oxygen in this water molecule. So it is pretty obvious. What they're asking us to find is like mass percentage. Then how should I actually consider over here? Percentage, if you get like percentage, it should be clear I'll have to multiply it with 100, right? So in both those situations, I'll multiply it with 100 to get the percentage. If I have to get the mass percentage, if I take like 18 grams, so that will be the 1 mole that I'm going to consider, right? So in both those situations, in the denominator, you'll get the total mass for 1 mole. So from this point on, we will consider 1 mole to be the standard quantity to study chemistry, chemical equation, whatever it is. So if I have to consider like 1 mole of H2O, that will be equal to 18 gram, isn't it? In the numerator, then obviously I'll have to substitute here what was the gram of hydrogen present in it. So in 1 mole, how did I get like how did I get like 12 gram, 18 grams? It was like 16 gram with respect to oxygen. That was the weight produced by the oxygen. Same way with respect to hydrogen, I have got like 2 grams, right? So 2 gram divided by 18 gram will give you the amount of percentage of hydrogen, mass percentage of hydrogen present in this 18 gram of H2O molecule. Okay, so that will give you 12 divided by 18 gram. So this is how generally we do the ratios, right, to get the percentage. So this will give you the mass percentage of hydrogen. Same way, if you have to get the mass percentage of oxygen, that will be the mass of oxygen present divided by the total mass of that molecule or compound. So that will be 16 gram divided by 18 gram. So I have just wrote the answer straight away. That will be like 11.1 percentage and then 88.9 percentage with respect to oxygen. Got it? So what will be the general formula for the mass percentage of the element? It will be something like this: mass. So that will give you, here I have just substituted the molar mass, isn't it? 2 gram was the molar mass of hydrogen, say H2, same way 16 was the molar mass of the oxygen, right? So molar mass of the element, molar mass of the element. So this is the molar mass. So I'll have to substitute in terms of G. Okay, so molar mass of the element in the compound. Okay, so what was the divided by molar mass of that entire compound, isn't it? So first I'll have to consider that particular element that will be in the numerator. So entire mass will be in the denominator. That's when I'll be able to get the percentage, isn't it? That's how I do the percentage, obviously. So molar mass of the compound, which will be in the denominator. So into 100 will give you the percentage. Yes, you should be clear with this one. Then I'm just going to tell you what is meant by solution, solute and solvent. Here, so these three terms will come more often in chemistry. You'll have to be clear with this term. So here I have taken a solution. Let me consider it to be water and I'm just going to mix some salt into it. Let's take the table salt, which is like NaCl. So the table salt that I've chosen is actually the solute. The substance that I'm going to put into it is called as solute, and the mixture, the water or whatever medium that I've taken will be the solvent. Okay, so something that I'm going to put it into into that liquid is actually the solute. Okay, so this will be the solute. Okay, the NaCl is a solute over here, and the water which is going to dissolve this solute is actually the solvent. Okay, solvent will dissolve this solute, which will be water in this case. So this one is solvent. Okay, so after the dissolution of this solute into the solvent, together solute and solvent is called a solution. So when they tell you solution, it simply means I have mixed the solute into it. Fine. So solution is the combination of both solute and then the solvent. Okay, so solute plus solvent will give you the solution. Fine. So these terms are very much required to learn the next other stuff. So next we will see mass percentage or weight percentage, volume percentage, and then the mass by volume percent. Okay, so here if I have to get the mass percent with respect to the a solution that we have learned, because generally when you do the experiment in chemistry, what we do is we just take certain substance as a solvent. Generally in majority of the situation that will be like water. There are some situation where you take some other acid as your solvent. Okay, so you have taken that solution, you have taken that solvent, and then you are going to mix salt or anything else into it. So once you stir it, it becomes a solution. Fine. So how much amount of solute I have added? So to get that understanding behind it, so to relate it in terms of math, what we do is we have just introduced some different terms into it. So that will be like person calculating. This is a kind of normal one: mass percentage, volume percentage. Then you have got like molarity, molality, mole fraction. So we will learn all those terms that are needed for us all for us chapters. Got it? Here you have got mass percent or weight percentage. So it should be pretty obvious. Here what I'm going to do is just the simple straight away one, which will be like something has to be in the, if I have to get the percentage, obviously this is like weight percentage, therefore it should be like weight divided by weight percent, right? So weight by weight percentage. Generally in the previous situation, how did I consider it is I took mass of the solute or mass of that particular element in the numerator, same way molar mass in the denominator, right? So same way I'm going to consider over here. In the numerator, you'll have mass of the solute that I added into the solution, that I added it into the solvent, okay? So in the numerator, you will have mass of solute divided by the entire mixture. So the entire mixture over here is the solution. So divided by mass of solution. So generally, when you have to find the fraction in the denominator, you'll end up putting the entire term, isn't it? So here, that entire stuff is the solution, not the solvent. Therefore, mass of solute divided by mass of solution will give you like weight by weight percentage. Got it? Same way, for the volume percent, what will I obviously do? Volume of solute should be in the numerator. That is something that I have added, divided by the total mixture, which will be the volume of the solution, right? So in the numerator, you will have volume of solute divided by volume of solution. So that will give you volume percentage, which is like V by V. We rarely use this one. In most often situation, we will not use this volume percentage. So that will be like V by V percentage. In some cases, weight by weight percentage is possible because that significant difference in the volume is hard to measure. So V by V percentage is one of the term that is good to know. Then you have got mass by volume percentage. So this is something that we generally use. Okay. So here mass will be in the numerator. Obviously, volume will be in the denominator. So this will give you mass will be in the numerator, which will be like weight W divided by V percentage. Okay. So in chemistry, you do not want to worry about the difference between the weight and the mass. If I tell you weight, it is simply the mass that I'm telling you, right? Okay, even if I use the term interchangeably, do not want to worry about it. Here you have got mass of the solute in the numerator. That will be this one. Mass of solute in the numerator. Same way you'll have volume of solution in the denominator. So now comes the tricky part. So here you do not want to worry about the units, because whatever unit that I substitute in the numerator, I'll have to use the same units in the denominator. If I substitute like kg in the denominator, also it will be kg. Here, if I take in liters, denominator will be in liters. If I take in meter cube, the denominator will also be in meter cube. It's the three-dimensional space that's going to occupy, isn't it? So volume by volume of solute divided by volume of solution, it's going to be same unit. But in the situation, that's not the case. In the numerator, I have some other term. I'm just going to divide it with some other term. Okay, so here it is like mass, here it is like volume. Fine. So what should be the units that I need to stick to? That's what I'll have to fix it over here. So generally, how will I measure the solute, the crystal salt or whatever it is? How will I actually measure it? I'll measure it in terms of grams. So that's the standard convention for doing experiment, isn't it? Therefore, in the numerator, that will be like gram. In the denominator, volume of solution should be taken in terms of milliliters. Okay, so we should be clear with this stuff. So in the denominator, I'll just divide it with milliliters. Fine. So 1 liter will be equal to 1000 centimeter cube, or else you could match it this way: 1 meter cube will be equal to 1000 liters, right? You should be clear with this convention and the unit conversion, all those stuff. We have discussed this one exhaustively in the physics part, so you shouldn't have any doubt or confusion in that stuff. So 1 milliliter, 1 liter will be equal to, I mean, 1 meter cube will be equal to 1000 liters. So from that, I'll be able to get the conversion if needed. Got it? So mass of solute should be taken in grams divided by volume of solution, that has to be considered in the unit of milliliters. Fine. So this will be the convention. Most often we will use, like, whenever they give you percentage in the question, most often that's going to be like mass by volume percentage. When you just read the question, it will become obvious. Mass will be given, solute will be given in terms of mass, whereas the solution will be given in terms of milliliters or liters. If I do the conversion, I'll be able to get the mass of solute divided by volume of solution. Rarely you'll get mass by mass percent. You will never get like volume percent. You can keep it that way itself. Anyway, whenever they're asking you to find the percentage, this is how you will have to do. In the denominator, you should always have the solution. Same way in the numerator, you should have the solute. Okay, so you should be clear with this part. Then we will see like mole fraction. So if the name itself clearly suggests, everything has to be in terms of moles. Okay, so everything has to be in terms of the number of count of molecules or atoms. Fine. So counting molecules or atoms is such a hectic one, therefore it is not possible. Therefore we have used this mole concept. So 1 mole is equal to such a humongous quantity of atoms or molecule, which is like 10 power 23. So 10 power 23 is obviously such a huge quantity, isn't it? 10 power 5 in itself is like 1 lakh. Then 10 power 23 is such a huge quantity, so that much amount of quantity will be equal to 1 mole, right? Got it? So here what I have to find is, I'll have to get the mole fraction. So to get the mole fraction, I've got two different solute that I'm going to mix into this solvent. So initially I've got Na, that was the number of moles of A crystal that I've taken. Same way Nb will be the number of moles of B crystal that I've chosen over here, and then I'm going to dissolve it in a solvent which has number of moles equal to Nc. Fine. So after the dissolution, the moles of the number of moles of solution will be equal to Na plus Nb plus Nc. So to get the mole fraction of A, I'll just put number of moles of A in the numerator. Same way, total number of moles of solution in the denominator, isn't it? So in the numerator, you will have number of moles of A, that will be in the numerator. Same way, total number of moles of solution will be in the denominator. So total number of moles of solution, isn't it? So this will give you the mole fraction. So the symbol that I use to designate mole fraction will be chi. Okay, so it's a kind of chi. That's how we need to pronounce it. It's like chi A. So chi A will give you number of moles of A divided by number of moles of total solution. Got it? So number of moles of A is nothing but Na, that will be in the numerator, and then in the denominator I'll have to add all those moles, which will be like Na plus Nb plus Nc. So this will give you the chi A. So chi A will look like elongated X, something of that sort. So next, if I have to get the chi B, which is the mole fraction of B, then how should it actually be is number of moles of B divided by number of moles of solution. So that will give you number of moles of B, that will be in the numerator. Same way you'll have total mole of the solution, total moles of solution, which will be in the denominator, right? So this is what is meant by mole fraction. So same logic and same understanding. Then finally we have got these two terms, molarity and then the molality. So molality you rarely encounter in the question. Okay, you don't see this term more often. But with the case of molarity, you will get this term again and again in chemistry. So you'll have to know what is meant by molarity. So when you consider molarity, it is nothing but the solute divided by solution. So in all the fractions that we took, in the denominator, it was always the solution, right? So molarity also goes the same way. I'll have to divide solute divided by the solution. So in the solute, which means in the numerator, it is like molarity. Therefore, obviously, it has to be number of moles of solute. Same thing like that of the mole fraction. So in the numerator, whatever particular solute they're asking, I'll have to get the number of moles of that particular solute, which will be in the numerator. That should be number of moles of solute, that will be in the numerator, but in the case of the denominator, that will be like volume of solution. Solution is the entire quantity, not the solvent, solution. So that will be in the denominator, which will be volume of solution. After mixing the solute, I'll get the solution, volume of solution. This has to be considered in liters. It is not in milliliter, but in the case of weight by volume percentage, there I took milliliter in the denominator, but in the situation. So this is the convention that we will see more often. Rarely they'll give you like weight by volume percentage. So that's a very rare situation. Only in the first chapter you'll get that weight by volume percentage stuff. But generally, in all the chemistry experiment that we see in the organic chemistry or the physical chemistry, whatever it is, they'll give you like 1 mole, 2 mole, take this quantity in 1 molarity or 2 molarity. So this will be designated by capital M. Okay. So if they give you such and such convention, then it simply means I have just dissolved so much amount of grams of solute in the 1 liter of solution. So that's the notion that you need to know. Okay. So number of moles of solute should be in the numerator. Same way volume of solution, it has to be taken in the measurement of liters. Fine. So then in the denominator, you'll have volume of solution in liters. Got it? But you should be clear with this mass by volume percent that we have considered. In here, in the situation, I just divided it by milliliter, but in the case of molarity, I just took like liters. Fine. So this is the convention that we stuck to. So you'll have to by heart it in this fashion itself, right? So this is what is meant by molarity. The final one is like molality. Okay. So same for the molality, you get the same thing again, which is number of moles of solute, that will be in the numerator. Same way in the denominator, you won't have like solution. So that was the normal consideration every time that we do. But in this molality case, that's not how we do the division. In the denominator, you will have solvent. That too, I'll take the solvent in terms of mass. Okay. So number of moles of solute divided by mass, it's not the volume. Okay. You should be clear. Here you have got like mass of, it's going to be like solvent. Okay, mass of solvent. So generally in this case, I'll stick to the SI unit itself. Therefore, mass of solvent in kg. Fine. In generalized cases, I'll just use the gram as my unit, right? But in this case, number of moles of solute, as usual, that will be in the numerator. In the denominator, it was not the solution. It was the before state, before dissolving solute into it. That is like mass of solvent. You'll have to consider the mass in terms of kg, right? So this is what is meant by molality, fine. So you should be clear with all these terms that we have discussed: molarity, molality, mole fraction, and then those percentage, mass by volume percentage, and all those stuff. You should be clear with all those things that we have discussed. Same way we did see what is meant by mole. Okay, so what should be equal to 1 mole? It will be equal to 6.023 into 10 power 23 of that particular entity. It could be atom or molecule or compound depending on the situation. Whatever it is, I just took that 6.023 into 10 power 23 from the carbon. By using the carbon, I defined, like I was able to define one atomic mass unit. So when you divide the 12 gram divided by the mass of one carbon atom, I ended up getting 6.023 into 10 power 23. So whatever the situation, if I have to take like different molecule or atom with respect to the same number of 1 mole of atom, then what will I have to do is I'll just have to take that much amount I'll have to take grams of atom in terms of molecular mass, okay, or the formula mass depending on the situation, right? So you should be clear with that idea that I'm telling you. Then what we did see, we did also see the average atomic mass, right? So those were the stuff that we did discuss in this session, you should be clear with all the concepts that I've told you, right? So we'll do PYQ in the next sessions. So PYQ, we will need around like 3 sessions to complete the PYQ. While doing PYQ, it will be such that the solving part will be lengthier, but the understanding and concept, this much is sufficient for this particular chapter, right? You shouldn't have any doubt in whatever topics that we have discussed. It should be clear. With this, the video gets completed. Bye.